Hello, I am Rui Cardoso, Senior Lecturer for Aerospace Engineering. This face you are seeing there is my face, and I'm going to introduce you to statics. So I'm going to show you some sample lectures and tutorials on statics. So if you want, for some reason, to email me with any query, you have my email address here. You also have these Instagram, Snapchat, Facebook, Twitter, things for Brunel, which you can try to follow. So what I'm going to cover in these sample lectures and tutorials is basically material for your year 1 at Brunel. So I'm going to cover statics only. Of course, you are going to do many other things, but the main topics I would like you to focus is basically the first three: vector analysis. I'm going to give a very quick review of vector analysis with the basics. And then I'm going to move to equilibrium of a particle, where a lot of vector analysis is required. Then I will introduce moment produced by a force vector. So these are quite basic but extremely important concepts that you need to know very well for the remaining of your lectures. Then I will move to the equivalent system force moment, where you will learn how to basically build an equivalent system that is in the same equilibrium conditions as the original system. That will be very important for the topic that follows, which is equilibrium of rigid bodies, which is the main topic in statics. We will study many different types of supports. The bodies or the rigid bodies, they need to have supports. They cannot be levitating in the air. And then we are going to learn how to replace those supports with forces, which are called reactions. And we are going to learn how to derive the equilibrium equations. Basically, these equilibrium equations will make sure that your body is in equilibrium. And then from those equilibrium equations, you can calculate many different unknowns. Then we will talk a little bit about beams. We will derive the transverse shear force and bending moment diagrams for beams. So this is a kind of introductory video I will have for all these sample lectures. Of course, different lectures will have this same introductory video, but they will refer to different topics on this table of contents if you want. Another thing you can, if you are more curious, I have a YouTube channel which you can, if you are interested of course and curious, you can try to see what I have there. So I have a lot of lectures in that YouTube channel, so you can search for that channel by googling Rui Cardoso YouTube. I have lectures for more advanced years, so I recommend at this point you not to see those lectures. But I also have some supporting material for statics in year 1 there in the YouTube channel. So I think is a nice thing for you to see as well. I would like also to say that all the examples I will be doing in these lectures and tutorials, not all of them, but many of them were taken from these recommended books I have listed here in this slide. So Engineering Mechanics Statics from Ibler, or from Vector Mechanics for Engineers, Statics from Beer and Johnson, from Engineering Mechanics Statics from Marian, Bolton and Craig, and also from my own book, Stress Analysis for Lightweight Structures, a MATLAB-oriented approach. So all the examples you will see in the videos, sometimes I refer which book I've taken the example, sometimes I don't, but these are the books that I follow. So in case I forget to mention which book I took the example, you have here the list of books, so you know where they came from. Right, thank you. So we will move now to the specific lecture. And this example is very important. I decided to choose this example because, yeah, you have some question?
Does this question involve turning moments?
No, not yet. This is the equilibrium of a particle. Equilibrium of a particle is only summation of forces equal to 0. We are going now, next week, to do the equilibrium of 3D rigid bodies, and we will need to have the moments, okay? But not yet so far, right? Okay, so why I choose this example? Because in this example, for example, what I want to show you, clearly show you here is, if you decide to do the free body diagram of this point E, if you decide to isolate this point E and represent all the forces that you have in this point E, we can do it here very quickly. Look at this. What is going to happen is, this is point E. Which forces do I have in this point E? I have force in cable ED. Right? What else do I have in this point E? The weight, right? Which is, sorry? You said the weight, right? Yeah. Let me represent the weight first. So we have the weight here. This is going to be the mass of cylinder A, which is unknown. That's what we are looking for, is unknown. Is in the question, right? Is here in the question. Determine the mass of cylinder A. So this is unknown, the mass of cylinder A. So I need to multiply the mass by the acceleration of gravity, which is 9.81. And then we have, like you said, we have the force in cable EB. All agree with me? We need to add also cable ED. Sorry, EB. EB. So we have, which you don't know. We don't know, right? We don't know the force in cable EB. We don't know the force in cable EB. We don't know the mass of our cylinder A. So if you do here a very quick balance of the unknowns that you have and the equilibrium equations, I'm going to write like this: equilibrium equations. How many unknowns and equilibrium equations do you have? Unknowns, we have 3, which are FED, FEB, and the mass of cylinder A. Equilibrium equations. This is a 2-dimensional problem. Equilibrium of a particle. I have only 2 equilibrium equations, which are summation of forces in the x direction equal to 0, summation of forces in the y direction equal to 0. This means, if I choose point E, I cannot solve my problem. I don't have enough equilibrium equations. So it means what? It means I need to get help from other points in my structure. In this case, point B. Right? So what I need to do is, I need to, let me see if I can. Let me move this one a little bit. Let me move this one as well. Okay. If you look at this cable, so basically you have the cable like this, right? So you will have, here you will have 40 times 9.81, which is the weight. Here you have the force in cable EB, right? And then you have here your pulley and your support. Carefully, I am cutting this cable here. That's why I have this force FEB, because I'm cutting the cable. And I am cutting this cable here and then I have this force which is equal to the weight of the cylinder, right? And because this is a cable, the tension in the cable is equal all over the cable, so we can say that the norm of FEB is going to be equal to 40 times 9.81, right? It's the same force in the cable.
Can you say that for the support, Fx equal to Fy?
Sorry?
Could we say that for the support, Fx is equal to Fy? The reactions.
No. For the support, you are talking about the support at B, right?
Yeah.
Bx and By.
Yeah.
Yeah, you need to do the equilibrium then. Once you have this, so if you want to calculate the reactions at support, once you calculate FEB, that you have FEB, what you do now is you put point B, you put your Bx, By, right? And then you have here 40 times 9.81, and you have here your FEB, which is also 40 times 9.81. If you look at this, right? You see, but basically what I'm doing is now I'm isolating point B. I'm also removing the support and replacing the support with the reactions. That's what we all. Just a moment. Let me just finish it. So in this case, look at this. You have two unknowns, which are Bx, By, and then you have two equilibrium equations, right? Summation of forces in the x direction equal to 0. Summation of forces in the y direction equal to 0. You obtain Bx, By. So they are not 0, the reactions, right? If the reactions are 0, it means the supporting is doing nothing there. It's like if you don't have any support, right? You were saying something.
Aren't you ignoring like the vertical and horizontal components of FEV and you're just making it equal to the downward?
I'm not ignoring.
But you just made it equal to I don't
No,
know.
I made it equal because this is a cable, right?
Yeah.
So when you have a cable, the tension you have the same tension at every point of the cable, right? So the tension or the force in this point, is equal to the force in this point, equal to the force in this point, equal to this, because it's a cable, okay?
Yeah.
But I'm not ignoring any component horizontal and vertical, okay?
Yeah.
They are there, right?
Yeah.
For example, now here, in this, to calculate the reactions Bx and By, if you use the equilibrium equations, you need to decompose the tension in the cable into a horizontal and vertical components, right? To obtain the, you know what I mean?
Yeah.
So I'm not ignoring that. All right, so okay, so let's continue this example. So we have the force in cable EB, so which is FEB. How much is it? Can you please do 40 times 9.81? 392.4 newtons. And now what we do is we replace. So this force here is going to be. So it's the same cable. Look, again, same thing, right? Cable FEB. So the force in this cable, in this point, or the force in this point, or the force in this point, or the force acting here on point E from the cable EB is going to be 392.4 newtons, right? Okay. So now that we have this force, we can now use the two equilibrium equations for this example. So I need to find some space. I'm going to delete this. Let's see. Okay. So now, let's work these vectors now. So we need a coordinate system, x, y. So let's start with the weight. So the weight is in the vertical direction only, so we don't have any horizontal component. The vertical one is going to be negative, right? So minus 9.81 MA. So this is the weight vector. Let's include now the vector for the horizontal force FED. FED is opposite to X, so it needs to be negative. Right? So minus FED. FED is still unknown. So we don't know the value of FED. And now we need to decompose this force in cable EB into a horizontal and vertical component. These ones I'm doing in blue. So this angle is 30 degrees. You can see here, right? 30 degrees. Agree? So this is 30 degrees. I'm going to include it here. So let's start with the horizontal one. How much is the horizontal? You tell me. $392.4 times cos 30. And the vertical component? How much is it? Times sine, correct? That's all the forces we have for this free body diagram, right? So in order for this to be in equilibrium, we need to have this equal to 0. Look at this. We have one unknown FED, second unknown, the mass of cylinder A, and we have two equations. First equation is this one, which will give us minus FED plus 392.4 cosine of 30 degrees needs to be equal to 0. First equilibrium equation. Second equilibrium equation is the vertical components of the resultant of the forces, which is minus 9.81 times the mass of cylinder A plus 392.4 sine of 30 equal to 0. Okay? So if we solve these two equilibrium equations, we get FED and we get the mass of cylinder A. In this example, the only thing we were looking for, I think, was the mass of cylinder A to keep or to hold the assembly in the position shown. Basically what they're saying is to get the equilibrium, right? So, that's it. You can now just get these numbers at home very easily. So just to summarize this example. So I tried to show you, the goal of this example was to show you how we can use different free body diagrams to obtain our equilibrium equations. Every free body diagram or every particle we isolate will give us two equilibrium equations. So we need to do this balance between the unknowns we are looking for and the equilibrium equations we need.